We are group 3 today and we will talk to you about our project in the distributed system course. Our project is node health checking. Let me properly introduce about our team and the project we have been working on for the past few months. Our team consisting of 5 people. We have Mr. Ninh Han Quân as the coordinator. He works the cracking password and backend server. Mr. Nguyễn Duy Khánh is working with the SWIMPHI protocol and phi-accrual. Mr. Nguyễn Hà Khải, he works in the node discovering and node deletion part. Mr. Tô Hạnh Phúc, he works with debugging, manual testing, and node deletion. And I, Võ Minh Duy, work with the gossip protocol and the front end of the project. About node health checking. Node health checking is a process to ensure that all machines in a distributed system works properly and efficiently. A related work that we would like to reference is Zookeeper, Weight-Free Coordinator for Internet Scale System by Yahoo. The common approach is that all machines report to a central entity who will process the status of the members inside the network and pass them. But that would introduce a single point of failure, a bottleneck situation, where the central entity have to carry the workload of everything in the system. And when that entity becomes unavailable, the entire system will likely fall down with it. So, we have proposed another approach to tackle down the problem, where we use a decentralized structure so that there is no need for a central figure to manage the entire system, easily nullify the single point of failure problem.
One challenge in decentralized overlays is how new nodes join the network without causing excessive communication overhead or disrupting connectivity. If nodes continuously add neighbors, the network becomes expensive to maintain. If they have too few neighbors, the network becomes vulnerable to partitions. To address this problem, we designed NEMO, a decentralized neighbor discovery algorithm that maintains a fixed neighbor degree while preserving randomness and connectivity. The idea is simple. In small networks, a joining node connects to all existing nodes. In larger networks, existing nodes are already full. Instead of increasing network density, joining node connects to selected targets, and those targets contribute to existing neighbors through a controlled, efficient process. As a result, new nodes can continuously join the network while the average degree remains crowded. Now, let's look at the implementation. This method is the entry point of finding NEMO and consists of 3 steps: discover peers, create a plan, and execute the plan. The first step is peer discovery. The node broadcasts join requests and collects acknowledgements from existing members. To improve reliability, the process is repeated multiple times with a random backoff between attempts. It helps the node discover more peers and avoids many nodes joining in lockstep. The second step is creating a CHUALANH, which is the core of the algorithm. Acknowledgements are divided into 2 groups: nodes with available neighbor capacity and nodes whose neighbor lists are already full. We prioritize nodes with available capacity because they can immediately accept new connections. However, we also intentionally select some fully connected nodes because they are already well integrated into the overlay and can provide additional neighbors through the eviction mechanism. This hybrid strategy balances efficient joining with long-term network connectivity. Finally, the CHUALANH is executed. Depending on the selected target, the node either establishes a direct connection or performs a join and evict operation. After this step, new node becomes part of the overlay while the network maintains its bounded degree property. Together, these design choices allow Finding Nemo to support decentralized growth while preserving connectivity, limiting overhead, and reducing partition risk.
In this part of the project, I implemented a hybrid failure detection mechanism that combines twin-style hot-speed grouping with phi-accrual based suspicion estimation. First, I use Java virtual executor service to execute the property test periodically. This scheduler continuously triggers the failure detector so that each node can monitor its neighbor automatically. Next, the detector selects a target node and sends a hot speed request. The hot speed is set asynchronously using completable feature, allowing the detector to continue monitoring all the nodes while waiting for the response. If an acknowledgement is received, the detector records the hot speed interval and updates the node health information. These hot speed intervals are stored in a sliding window and later used by the phi-accrual algorithm. If the direct hot speed fails, the detector performs indirect verification. Several helper nodes attempt to contact the target node. This helps distinguish between a real node failure and a temporary network issue. If both direct and indirect verification fail, the detector calculates a phi value. The phi value represents how suspicious the node is compared to its normal hot speed behavior. The detector then converts the phi value into a node status. A node can be classified as alive, warning, suspected, or unreachable. When a node becomes suspected or unreachable, the information is propagated through the register system. This allows all nodes in the cluster to gradually converge to a consistent view of failure. And finally, when a node is classified as unreachable, recovery action are triggered to update the topology and restore missing connection.
Okay, so now let's come to the core implementation of the rewiring mechanism, which handles the node failure problem. As I described in the paper, we have two possible cases. The first one is when two diffusion nodes have not connected to each other before, so we just simply connect, and this code shows how it works. Here, it shows the case 1 in the paper, no existing connection, described in section D. Each direct rewiring session has its own ID. Then the node itself, which is called node A, sends a request to another diffusion node called node B. If the node B accepts the request, it will send a response including the accepted status back to node A. The actual implementation that connects the node A to B is the additive space method in Connection Manager class. Then node A sends a rewire message to the node B to inform it to create a direct connection via the additive space method itself. The second case is when the connection between two diffusion nodes has been established before. As I explained in the paper, we identify two random nodes called node C and D, and a connection between them has been created. Then we just break the connection and connect A to either C or D, and B to the remaining one. Here, this code shows the procedure. First of all, the current node A found another division node B that was already connected to A. The leader election algorithm is used to determine which node is a leader. We assume that node A is a leader, and then it sends a rewire message to node B to inform that it is a fellow node. Next, the node A finds some nodes denoted as C, which connect to A but do not connect to B. By observing the entire neighbor list of A and extracting all nodes that do not connect to all elements in the neighbor list of B. For each candidate C, the leader sends a request message containing the neighbor list of node A and B along with the current recovery status. Upon receiving the query, node C searches for a node D that is a neighbor of C but is not a neighbor of A. And finally, we just apply the algorithm described in the same case of section D.
Before we end the video, I would like to show you a demonstration of the network. I will now start the 5-phase evaluation plan as described in the report. With 7 initial nodes, the max neighbors is 4. Phase 4 will add 4 new nodes, and phase 5 will remove 3 nodes. After 35 seconds, all of the nodes are started and the evaluation will begin. As you can see here, only 15 seconds later, all nodes have 4 neighbors each except for node H143. This case is explained in detail in the report. All you need to know is that this behavior is expected. We will now wait until the phase 1 timeout is over and the recovery phase will begin. The recovery phase will now begin. The deficient node H143 is restarted. For the sake of simplicity, a node with a different name is started instead of using the same name, SR59. The network has stabilized. You can see that there are 7 nodes, all of them have 4 neighbors each. Phase 2 is starting now, and node G139 is chosen randomly to be deleted. After 9 seconds, the system has received 1 report. At 27 seconds, the system has received all reports from G139's neighbors. "13 seconds later, every node has successfully removed G139 from their neighbors list and have found themselves a new neighbor. Phase 3 is complete. Phase 4 is starting and 4 new nodes are being added. Phase 4 succeeds in 16 seconds after the last node has been added. In phase 5, 3 nodes will be randomly deleted at the same time. After 40 seconds, the network converges. The evaluation has completed successfully, and I hope this evaluation has demonstrated the effectiveness of the algorithms proposed as well as provide a visual representation of the algorithms. Thank you very much for watching this video.